Today on Macaulay Math, we're talking derivatives of exponential and logarithmic functions. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200 Calculus 1, Lesson 10 on the derivative of logarithmic and exponential functions. Our goals for today. We're going to derive exponential functions involving the natural number e. We're going to derive exponential functions involving bases other than e. And we're going to derive logarithmic functions. In this lesson, we explore the rules for finding the derivatives of exponential and logarithmic functions. Additionally, this lesson provides opportunities to review the product rule, the quotient rule, the chain rule that we learned in previous lessons. Let's get started. The natural number e and the natural logarithm ln. The natural number, or Euler's number, e, can be defined in multiple ways. In pre-calculus, we defined the natural number in terms of a limit, and that limit was to let the expression 1 plus 1 over x to the x go to infinity, and when you do that, you end up with a number close to e. And the natural number is defined from pre-calculus as y equals ln x as the inverse of e to the x. Calculus defines ln x as ln x is equal to the integral from 1 to x of 1 over t dt, where x is greater than 0. And I should note that this notation will be discussed later in the course. And so therefore, the derivative of the natural logarithm, d over dx of ln x, is just going to be 1 over x. And the derivative of ln of some expression u that's in terms of x will be the derivative with respect of x of ln of u will be equal to 1 over u, whatever that expression will be, times the derivative of that expression, times the derivative of that expression with respect to x. If we have an absolute value, we don't have a whole lot to worry about, but the derivative with respect of x of ln, the absolute value of u, will be 1 over u times the derivative of u with respect to x. Some properties of logarithms. This is a review from what we did in Algebra II. And so the natural logarithm of 1 will be 0. In fact, a logarithm with any base of 1 will be 0. The ln of a times b will be equal to the ln of a plus the ln of b. The ln of a to the n, we can bring that n down in front and say it's n ln a. And the natural logarithm of the quotient of two expressions will be equal to the natural logarithm of the numerator minus the natural logarithm of the denominator. Now, the reason we go over these properties of logarithms is that they can be used to manipulate functions before you actually differentiate in an effort to make that differentiation easier. So our first example here, we're going to take the derivative of ln of the quantity 2x plus 1. Now, when we go to do that, we'll notice that this is the composition of ln of x and the 2x plus 1. So we have a composition here, so it's going to need a chain rule. So that's what that d over dx of the quantity ln u equal to 1 over u times du over dx is. It is an example of the chain rule. So the way that we apply this is the first derivative with respect to x, we're going to say let u equal the 2x plus 1. And so if the u is the 2x plus 1, then the first derivative here will be 1 over 2x plus 1, and then we have to multiply that by the derivative of whatever u with respect to x is. So in this case, if I take the derivative of u with respect to x, the derivative of 2x plus 1, well, that's just 2. So I'm going to multiply by 2. And so my final answer here, f prime of x, is just going to be 2 over 2x plus 1. That is it. That's all I can do with that one. My next example, and the reason I'm doing this as an example is because I actually want to do it two different ways. And the first way is I want to do it as a composition, similarly to the way we did it in the last example. And so the way I'm going to do that is I'm going to say f of x is equal to the ln of x to the fourth. And in this case, I'm going to say let u equal x to the fourth, and then du over dx will be just the derivative of this thing, which will be 4x to the third. All right, so we want to do that. The f prime here in this case will be 1 over x to the fourth, we left that alone, times the derivative, which will be 4x to the third. Now when I look at that, I'll notice that I have 4 x's in the denominator, I have 3 x's in the numerator, so 3 of those x's cancel, and when I simplify this thing, I'll have 4 over x as my final answer, and that is the derivative. Now the reason I picked this one is because we can also use one of those properties of logarithms to simplify it before we actually do the derivative. So let's look at it in a different way, and we'll start with that same function, f of x equals ln of x to the fourth. But here, before I actually do the derivative, I'm going to apply the rule that says the ln of a to the n is equal to n ln a. And so we can do that. So I'm not taking the derivative yet, so I don't need the f prime, but I'm going to bring that 4 down and say it's 4 times the ln of x. All right, so now I want to do the derivative. And since this is now a constant out in front, it stays alone by itself. And then the derivative of just ln x is just 1 over x. And then when I simplify that thing, I again get 4 over x. So there's a number of different ways that you can manipulate functions using properties of logarithms to get to your final answer. The next example. And in this case, I'm going to apply a bunch of those properties of logarithms before to help simplify this, because I could do this in a bunch of different ways. I could look at this thing as if it were a large composition. I could do the ln of something to the fourth power, and then I could do the derivative of the quotient. I have 3 different functions I could change. That seems to be overly complex to me. So here's what I'm going to do. I'm going to apply a bunch of different rules first. I'm going to use the ln of a to the n equals n ln a rule. And then I'm also going to use, since I have this quotient here, I'm going to say that the ln of a over b is equal to the ln of a minus the ln of b. I'm going to use both of those. So let's do them in steps before we actually do the derivative. And I'm not doing the derivative, so I'm not going to write g prime. So my first rewrite is going to be 4 ln of 2x over x plus 1. And then I'm going to say that g of x is now 4 times the quantity, the ln of 2x, minus the ln of the quantity x plus 1. Now, I've done all that work so that I won't have to do that multiple steps of chain rule, and I won't have to do a quotient rule when I get down to this innermost function here. So now I'm going to take the derivative, so I'm going to write my g prime. I'm going to leave that 4 out front. So even though that I have simplified this, it is still not just the ln of x. It is a composition of ln with some u function 2x. So I'm still going to have to use that chain rule. And I have to write it as 1 over 2x times the derivative of 2x, which would just be 2. And then I'm going to subtract 1 over this expression, so x plus 1 times the derivative of x plus 1, which is just going to be 1. And I should simplify this a little bit. So let's see here. My 2's will cancel, and then when I distribute the 4, I'll have 4 over x, and then 1 times anything is just that expression. And when I distribute the 4, it'll go on the top, so I'll have minus 4 over x plus 1. Now, we could simplify this further, and we could make it into a single fraction, but it is usable, and we do have some other examples to move on to. My next example is one where I'm going to use logarithmic differentiation to find dy over dx. And if you look at this particular expression here, I have a lot going on. I have a quotient of two functions, and each of those two functions are the composition of an inner function with some exponential. This one 3x, and then the squared is the exponential, and then this one will have x squared plus 1 all to the 1/2 power. I am actually going to add some logarithms here so that I can apply those rules, simplify my expression a little bit, and get to my derivative a little bit easier. So my first step in this particular case is I am going to take the ln of both sides. The ln of y is equal to the ln of this big expression. So quantity x plus 3 squared over, and I'm going to rewrite the bottom one, x squared plus 1 to the 1/2. All right, so now I'm going to apply those properties. I'm going to, just like in the last one, I'm going to apply both the ln of a to the n equals n ln a, and I'm going to apply the ln of a over b equals the ln of a minus the ln of b. And so that'll give me ln of y is equal to the ln of x plus 3 squared minus the ln of x squared plus 1 to the 1/2 power. And then let's go again and bring those exponents down. So the ln of y equals 2 ln of x plus 3 minus 1/2 ln of x squared plus 1. All right, so now we're going to take the derivative of the whole thing. So d over dx ln y equal to 2 ln x plus 3 minus 1/2 ln x squared plus 1. All right, we're going to treat this y, since it's not in terms of x, we're going to treat this y as if it were a u function. All right, so just like when we said the derivative with respect of x of the ln of u was equal to 1 over u times du over dx. Well, we're just going to change that to a y for now. And we'll say that this is 1 over y times dy over dx. Now, dy over dx, that's what we're looking for. Because if we go back up to here, we're doing the derivative of y. So we're trying to find dy over dx. So this portion right here, that's what we're looking for. When I get that by itself, we'll be done. All right, so the derivative of this second term, I'll leave the 2 alone, and then I'm going to go 1 over what's inside, so x plus 3 times the derivative of that expression, which is just 1, and then minus, I leave the half alone, times 1 over that expression left by itself, which will be x squared plus 1, and then multiply by the derivative of what's inside, which will be 2x. And I need to simplify. Let's simplify this down. So I've got 1 over y times dy over dx will be equal to, let's see here, 2 times 1 will be 2 in the numerator, and I'll have x plus 3 in the denominator. I have a half and a 2 that cancels out, so this just becomes 1 over x squared plus 1. And so now I'm going to multiply both sides by y. All right, extend the page. And so I'll have dy over dx equals y times the quantity 2 over x plus 3 minus 1 over x squared plus 1. And so this y is the same as the y equals. So I'm just going to rewrite y. Here I will substitute the original y. And I'll have dy over dx is equal to the original function, which was x plus 3 quantity squared over x squared plus 1 to the 1/2 times this expression, 2 over x plus 3 minus 1 over x squared plus 1. Now again, I'm sure that if I wanted to, I could simplify this expression, but just to keep this lesson short, I will leave it there and move on to my next example. The derivative of a natural exponential function, and this one's kind of a funkadoo, but if you'd like to see the proof, you can always check the links in the description below. And the derivative of e to the x with respect to the x is just e to the x. And so we have a function whose slopes of tangent lines is equal to the value of the function anywhere on that tangent line, which is kind of crazy. The derivative with respect to x of e to some expression u is, and this is again the chain rule expression, is the derivative of e to the u times du over dx. And so my first example of the derivative of the natural number is f of x is equal to e to the x squared. So here we're going to apply the derivative with respect to x of e to the u, because it's not just an e to the x function. That is an expression itself. And we remember from the last page that that's going to be equal to e to the u times du over dx. Now in this particular instance, we're going to let u equal x squared, and then du over dx will be the derivative of that, which is going to be 2x. So my first derivative here will be, we'll leave the original function alone, so it'll be e to the x squared times the derivative of that, which will be 2x. And we could leave this as is, but just for my own personal sense of order, I'm going to rewrite this as 2x times e to the x squared, and that'll be my solution for that. Next, differentiation rules for bases other than e. So if I want to take the derivative of an exponential that has something other than e in it, the derivative of any base other than e to the x is going to be the ln of that base times that expression again. And then similarly, we have the chain rule example here. So if I have the derivative of any exponential base other than e to some expression will be the derivative of that base times the expression left alone times the derivative of whatever that expression is. So let's do an example of that. And so here we've got a few things going on. We're going to have a quotient rule. And then, so we have a quotient rule. And then we have a derivative with respect to x of e to the u. And then we also are going to need, and then we are also going to need d over dx of a to the u. And so we'll have to do all of those derivatives. So let's go g prime of x. So hody high. So the original function left alone, 5 to the 2x times the derivative of what's on top. So the derivative of e to the u is just going to be e to the u times du over dx. So we'll multiply that by we'll leave the 4x alone, times the derivative of 4x will just be 4, minus high e to the 4x times the derivative of the bottom. So this one is just going to be the ln of a times a to the u times du over dx. So in this case, our a value is 5. So it's going to be the ln of 5 times 5 to the 2x times the derivative of that, which will just be 2. And then that will be all over the bottom function squared. Okay, let's see. Can we simplify this at all? So here I'll have 4 times 5 to the 2x. And remember, we can't multiply these numbers. I see that as a mistake from students over and over because you'll be breaking the order of operations. If you multiply these two and make 20 to the 2x, then you'll be breaking the order of operations and you will be doing multiplication before you do exponents. So we have to leave that alone. And then that'll be times e to the 4x. And then we'll go minus, let's see here, we'll have 2 times the ln of 5 times 5 to the 2x times e to the 4x, and that will be all over 5, let's see here, to the 2x squared. Now the reason I didn't multiply these two, and you can actually do that, but you'll notice that I have, and I'm going to highlight it and I'll undo the highlight. Here I have a 5 to the 2x in each of those terms. So I can cancel out so I'll be left with 4e to the 4x minus 2 ln 5 times e to the 4x all over 5 to the 2x. And that is going to be my final answer. Well, folks, that's all I've got for today. So, the Star Wars fun fact of the day. The Emperor's chair from Return of the Jedi was mechanized so that it could rotate when the scene called for it. However, that mechanism never worked properly. So the actor Ian McDiarmid had to make it move by shuffling his feet. A piece of tape placed on the floor told him when it was time to stop, so it would not be visible to the camera. That's all I got for today, folks. Have a good day. Bye.